real strings, just like your shoelaces. Okay? What's a string? It's an object with azimuthal symmetry. It's a symmetry of a circle, right? You imagine a long, static, straight string. So when we found the domain wall, we looked for a solution that had a discrete symmetry, right? From, say, up to down, down to up. So it was logical to look for a model which there was a discrete symmetry, spontaneously broken. So if I want to find a solution with a circular symmetry, I should look at what kind of theory? U1. So let's try to see what happens in U1. So you see that there is a logical order. This is now finally something which is continuous. So Lagrangian would be d mu phi square. I have a complex field that carries charge under this U1 symmetry. That's not electromagnetism, by the way. It's our U1 example, which is spontaneously broken, the good old prototype of the Higgs mechanism. Okay, that's how it all started. So in a sense, it's another reason maybe that we should revisit it, right? That's how we learned about the Higgs mechanism. So let's see what would happen if the Higgs were realized in the U1 case that Higgs wrote down. By the way, I mentioned to you, and I even told you to look at the original work, but you may not have done, the non-abelian Higgs mechanism is attributed to whom, do you know? It's often attributed to Kibble and of course Weinberg. Because Higgs in his papers does U1. Actually he does more than U1. Did anybody look at it? I had mentioned it. Higgs in that original paper that made us call it the Higgs boson.
The one I read is SU2. The one I read is SU2.
SU2?
Yeah, he does theory. No, I read it.
No, it's called Weinberg.
It's Weinberg.
That's Weinberg.
Oh.
Weinberg does SU2.
I confused them.
Higgs does U1. Higgs wanted to illustrate, of course you are going to do U1, you won't do SU2. That's for sure. Whoever would have done this. But then he says, well, we could do even a non-abelian example. He takes SU3 with the adjoint. Your final exam problem. He didn't study it carefully because you remember there are subtleties there. It's not clear how the symmetry gets broken and so on, depending whether you put the cubic term. But anyway, this is his great work. I have a usual potential, right? Symmetry broken. And I want to find the classical solution, right, that I call strings. I wanted to have a finite energy. In other words, if I have a finite strings, I want to have a finite energy. If it's infinite, it's okay if the energy is infinite, as long as E over L is finite. You agree? For an infinite object, we don't worry that the energy is infinite. That's, of course, the usual extrapolation we do as physicists. So the energy would be integral over the right over rho and phi. And I want to find a static solution, remember, finite energy. So I would have terms like di phi squared plus v of phi plus, what do I get when I take the Hamiltonian? I get electric and magnetic field, right? Not the difference. I'll get 1/2 E squared plus B squared. Right, and I'm writing this. If I'm looking for a symmetric solution around the z-axis. So that's how we started with the Van wall, right? We asked that the energy is finite, so that means that each piece which is manifestly positive definite goes to 0. So in other words, when rho goes to infinity, di, let's look at the static one only, di phi goes to 0, v phi goes to 0, and this also goes to 0, electromagnetic field, which means that phi goes to phi infinity, let's say, becomes v squared.
How is the string situated in the space, in which direction?
Z.
It's like
Z.
a cylinder?
Z. This is my string. And I'm integrating around rho d rho 2 pi. Notice that immediately that we get the situation that we like those maps, famous map. Why? Because what is M infinity? It's a circle, rho going to infinity. Rho is some very large radius, r, very far. And also the vacuum manifold is circle. And phi at infinity might live in the vacuum manifold, right? What we are saying here, that phi at infinity belongs to vacuum manifold. And that's providing the map. I'm mapping an infinity to the vacuum manifold. And of course there is a trivial map always. I can take phi infinity to be V. I can take then phi to be V everywhere. That's called vacuum. Agreed? I'll get zero energy. Nothing exciting will happen.
Trivial solution.
Sorry?
It's a trivial solution.
It's a trivial solution, and it has to exist always. The non-trivial solution would be if I take phi at infinity to be V, it's a function of theta, e to the I theta, for example. This is non-trivial. Phi infinity, so let's say better goes to v to the I theta.
Theta is the coordinate.
Theta is the, let's call it phi. No, I have to call it theta, sorry.
Yeah.
Rho and theta are coordinates. Well, normally we would call phi, but we don't want to call the field. It's a pity actually, but okay. We have z, rho and theta, right? And z I have frozen.
We also consider static field here, right?
Static.
But all the
To generalize to moving is quite complicated, okay? This is, then I just want to establish static.
Being stable or not stable is similar to discussion.
I think it will be clear. I mean, you yourself were saying, for example, well, first you can ask me, can I take this everywhere? If I were to take this everywhere, it would look like a gauge transformation. This looks like a pure gauge, because then you... But obviously you cannot take it 0. Notice that phi at 0 must go to 0, otherwise it wouldn't be single value. At 0, you cannot say that at 0, what is it? We look for a solution, in other words, we look for the solution, let's call it phi, is phi string, is V, f of rho, e to the I theta. Well, f of rho is 0 when rho is 0, and f of rho is 1 when rho goes to infinity. That's what I mean by a string. And this, clearly the symmetry tells you that it's not a pure gauge. You see what happens by, I'm forced, the same thing happened with the domain wall. I couldn't, topology didn't allow me to have it V and minus V. It had to go through 0. I'm paying a price. I will have to live somewhere in the maximum. When phi is 0, look at our potential, we are at the maximum of the energy, okay? That's what created the domain wall. Remember, domain wall is made out of phi, living away from its minimum. This is a string. I'm not going to write this expected function. It's not trivial to find it analytically. All we want is to establish the properties of this string. You will see why and how. Notice that nothing will go wrong if I put an integer n here. I want it to be single value, so I can't take any number. It better be n. Okay, this is a famous map that people talk about. The single value that forces this coefficient to be integer, because when you are 2 pi, you want to get the same thing. You want to be well-defined. Otherwise, when n is different from 1, it will be sort of some kind of multi-string solution we will call. I could put it there, and then we can look at n equal 1. You want to? Well, let's see how far we can carry this with n at the moment before. I also want the phi to be 0 at infinity. Therefore, AI goes as E1 over G di theta. G or E, sometimes people call it E. It's not E, it's G. This U1 is not the U1 of electromagnetics, so let's just call the coupling G. In other words, d mu phi. Phi is obviously complex, I don't have to write that. Carries charge. And I normalize it to carry charge 1. That's a definition of charge.
So now we say we want
we can put n here, sorry.
is this n? It's a pure gauge.
Well, at infinity.
Yes.
At infinity, yes. Not everywhere. If it were everywhere, then there would be no physics interesting, okay? This, like this guy, these are pure gauges, okay? Because this can be gauged away. This also is a pure gauge because I can perform a transformation gauge away, but I can't perform it everywhere. I don't have a regular, it will be some kind of singular transformation somewhere. Something somewhere will be happening, it will cost me energy. This is, pure gauge means that there is no energy stored. But you will see that the string will have to carry energy, okay? There is actually a string because at the origin, I'm forced to go to 0. It's a singular gauge transformation. So it's not a pure gauge. It looks like a pure gauge. And you get a remarkable, you will see how we get in a second a remarkable result. When there is non-trivial AI, I suspect that there is a non-trivial magnetic field. But let me see. BDS, what is BDS? It is ADL at infinity, you agree? Okay, Stokes theorem. What is this? Delta. I will get 2 pi. It's just delta theta. The integral is trivial. Di, dxi gives me delta theta. Let me write. This is n over g. Delta theta, which is 2 pi over gn. There is an n-trivial flux. There is really a physical string. There is a magnetic field. The symmetry tells you that there is a magnetic field. Of course, which direction is it pointing? Magnetic field inside the string, of course. Outside is lying, everything is going to 0 far away. The magnetic string is here. The magnetic field is the magnetic string. The magnetic field It's here. It's in the z direction, right? BDS is ADL. Match.
It says that
This-
this U1 is not electromagnetic, but we gauge our electromagnetic field with this data. Like our gauge transformations, the same data, we transform phi.
Well, it's spontaneously broken. It's not electromagnetism. I don't know what this is. I have to find that example. It's not easy. We can try to think in a second when U1 breaks. It's opposite from the standard model. In the standard model, U1 doesn't break. SU2 cross U1 breaks down to U1. See, standard model didn't have a discrete symmetry, doesn't have a string. Standard model is the most boring theory of all regarding topology of defects. It has nothing. So this is why this goes into the beyond the standard model physics.
When you say the integral of a field is yes, you mean that the magnetic field go out from the rod like this, not like this. So
Magnetic field is confined in the string.
Like from the poles of the sphere.
Magnetic field is flowing through the string.
but when
BDS is ADL. A goes around, not the field. The field goes this way. That's how. Field is the curl of A.
But there is a non-zero B.
I mean when you integrate
There's
over
a
the
non-zero B
surface-
in the z direction.
Listen, when we integrate over the surface, ds, we integrate over the surface of the cylinder, right?
No, the section. The
So-
long
Yeah,
section.
yeah, okay. The surface of the cylinder, the section,
No.
just
Oh, okay, that's okay, like this.
the section, right? The string is infinitely long. Just think of the little fellow playing there, okay? And we are finding that there is a electromagnetic field. Nambu had imagined that confinement could come from this, that the string would actually be going from quarks and anti-quarks. It's a kind of picture that we like to imagine, that we sort of like to think that there is some kind of, now is that there is no rigorous statement like that in QCD, but sort of that's an idea that quarks are confined because when you have a quark and anti-quark, okay, just imagine it is very long, not infinitely long, and there will be a magnetic field confined, and that sort of, and it costs you energy, so every time when you try to pull the quarks apart, the string breaks, and you form a pair of quark, anti-quark, it costs less energy. It was sort of inspired by this Nielsen-Olesen string, the picture the people like this explicit construction of a string solution. Late 60s, early 70s, I don't remember precisely, 71 I think. Now I didn't write the solution, but I would imagine some kind of exponential in-depth solution as we usually why, because there is a scale in the theory, that's a vacuum expectation value, so we'd imagine that the thickness of the guys, and they should come out, f of r should be some kind of exponential function. So instead of doing that, I don't have an analytic form. Let's use our energy reasoning to see why there is a string. Let's look at the energy to try to understand. So you see what happens inside the inside you go into phi equals 0, right? Inside the string. So let me now imagine sort of kind of step function, right? I'm inside and outside. Inside phi is equal 0. A equals 0. And B is something. I imagine it very thin, so I imagine a constant magnetic field. Of course, it probably varies with rho, but let's imagine it very thin. Or maybe A is not 0, I don't know when I say 0. It's irrelevant. And outside, phi is in this V, right?
The magnitude.
Sorry?
The magnitude.
Outside phi is, sorry, why did I? Outside phi is V, so I'm in the minimum. So the energy of this, let's look, the main contribution would be inside, I would have 1/2 V squared plus V of 0. This is what I have, integrating from 0 to delta. The energy is stored inside this thing. Outside, I'm in the vacuum. Now first, let's see how big B0 is. Oh, I forgot to write this. I have that flux. Okay, flux was BDS. What is BDS? That's B0 times, what's a surf? What's an area? Pi rho square, right? It's correct, right? It's a circle. Right? Thank you. That's equal to the flux. What was the flux? It was 2 pi over G. Let's take our n equal 1 string. Surely n equal 1 is stable, right? You can't unwind it. And n equal 2, you cannot unwind to n equal 1. Maybe n equal 2 can decay into 2 n equal 1. Then you start to think of energy considerations, right? But the topology tells you, this is what you guys told me, don't even look for the conserved charge. Don't worry about that, it's a waste of time. You know that when we had a domain wall that connected like this, it could never decay into a vacuum because it has a different topology completely. This also, if I go around the circle, that's a different map from a trivial one.
We are going to talk about decaying, like for example, as you mentioned, n equal 2 decaying to n equal 1, we should have, I mean, in that case we will need to add some terms to the potential, some interaction term.
I don't know if I have to add. N equal 2, I know, cannot decay into n equal 1. But I don't know a priori. I can only think topologically here, unless I really compute the energies of these solutions. I need these functions, you know, for a generic n. I compute it. Once you have the function, you compute the energy of the system, and then you see what can happen. You would have to compare the energy of two n equal 1 strings and n equal 2 strings. If n equal 2 string carries more energy, then why would it be stable? The rule of physics, as we know it, you decay unless you can. This is not rho square, this is delta square. The radius is delta, not rho, right? The thickness is.
Yes, and define the rho term, do we need to add also in the energy? The change of field step. Define the rho here. As we had in domain rho, the derivative of the field inside. Where is it?
No, it's a covariant derivative now. There was no covariant derivative. You see the advantage of this. If you look at the solution di phi going to 0, then we can look at the solution inside di phi 0. This will be smooth. Phi is equal 0 and di phi is 0 inside.
So we don't see the change since we are...
Right, because the covariant derivative is different now. The global strings, if you didn't have, people like to think even of global strings, okay, whatever that means. Then of course you're right. Then there will be the energy carried in the derivative. That would have to be non-zero. But the covariant derivative can be smooth. So B0 is how much? Is 2 over pi G delta squared, something like this. Maybe without pi is better. Okay. say so. I think it's true. So we would get, and this is a constant, we will get 2 pi. This is just an overall factor times whatever this is, delta square, right? Well, let's write it, delta square. What would the B0 square? I will have 1/2 times 2 is 4, I'll get 2 over g square delta to the 4th plus the potential. What do I have in the potential? That's lambda to the over 4v to the 4th times delta square, right?
Okay.
You agree?
Okay.
I'm just thinking of a very thin, and then we see that it's justified, very thin wall in which I'm inside, I'm in the maximum, outside, I'm in the minimum. So this is 2 pi. There are some common factors, but I didn't. The first piece goes as 1 over delta square up to the constants. Why don't we just write like this? Plus v to the 4th delta square. And you see how you get these solutions. You can think of them topologically, you can construct them, you can also think energetically. You see what happens is the magnetic field, of course, wants delta to be as large as possible. The bigger the delta is, then there is less of the flux. You see there is an incredibly concentrated flux in this thin wall. But the bigger this goes to 0, but then this goes to infinity, and they will match. So in other words, if I write that d over E over L over d delta is 0, I want to minimize the energy. That will be my solution. This goes, I will get 1 over delta cube here equal v to the 4th delta. It's what we expected. Lambda, I took 1 and g equal 1. There is a non-trivial interplay. The delta will always be 1 over v. Whatever we solutions find, whether it's domain wall, whether it's some spherically symmetric monopole that I'll call later, it's the only scale. It's good to see it explicitly, you know, it's always instructive. And that we would see the way we see domain wall. There must be so in some approximation, I'm sure you can find an exact analytical expression, okay, when you simplify g equal lambda or something. People I don't have a form, but it's exponential. F of rho will be something that is 1 minus e to the minus rho v, something like this maybe. It's going to be something like this.
I have a question about magnetic field. I think it's problematic to put magnetic field into z direction because what goes out from top also goes in from bottom, so we don't have a flux. So maybe it's something weird going on in the string.
This is an infinitely long string, so I'm not caused that problem. Otherwise I need something, as we are saying, some sources, but this is an infinitely long string. Of course it will be in the z direction. Which other direction there is?
It should somehow be
The symmetry of the problem tells you that it must be in the z direction. That's what the formula also tells you. BDS is equal AD. A is, well, I know where B is because A is here. So B is, right? When A is here, B is going up or down, depending depending whether I take n or minus n, right? There are strings, anti-strings, and so on, depending where they are. I can wind this in that direction.
I was thinking if you put a solenoid there, physical, we could produce the same thing. And standard Maxwell equations forbid magnetic monopoles.
Yeah, you will never get this in a how can you get it in
This
QED?
should be different than a solenoid that produces.
No, but this has nothing to do with QED. This cannot happen in QED.
Yes, this
Of course, the symmetry is broken, V is 0. How can you tell that? The string is, instead of saying that there is a string which is infinitely thick, there is no string. No, this is not that. That's, aha, I can see now what's bugging you. Your intuition is failing here. Of course, because in electromagnetism, again, this is not electromagnetism. So it's not a magnetic field of electromagnetism, right? It's associated field of something.
We sort of did a topological defect in standard electromagnetism, and we end up.
No, it's opposite from standard electromagnetism. It's opposite theory from standard electromagnetism.
Because we have that here, for example.
Right. It's something we don't know what it is. It's a sort of prototype of a W boson, only it's U1. So of course, you know, the physics of a massive, of a broken theory is different from the unbroken one. Everything is different. There is a long-range force here. There is not a long-range force. There is no photon that propagates. There is not. Everything breaks down to what it says. So I want you to think of what we could be. We have to think of some example. Not easy to imagine it, but with some knowledge of grand unification, for example, we could suspect. You know, there is a theory which people like, which is SO10. The minimal grand unified group would be SU5. That's easy to see. Then there is a big one, which is SO10. SO10 is big one that it contains SU5 and U1. Why? Because it's a rank bigger for 1. This has rank 4, this has rank 5, SO10. SO4 has rank 2. SO6 has rank 3. SO8 has rank 4, SO10 has rank 5. You can easily see those. Think of the generators of SO right there. And you can imagine, so imagine this happened. In other words, start with, if you don't care about that, and break this down to SU5, which is our favorite laboratory, not model, because it's the minimal. So we could imagine some situations in some theory where that happens. Okay, not so exciting, but possible. Okay, possible, this could have happened. So U1, which is broken opposite, precisely opposite from the standard model. In the standard model, I take SU2 cross U1, break it down to U1. Here I do the opposite. I take SU5 cross U1, I break it SU5. Here I will get strings. Let's try to see. You can say, well, should I worry if there are strings? I mean, we decided we would worry if there was a big domain wall, okay? Don't even worry how it would come there. Okay, we can ask the question just, you know, I'm just scared. These objects are funny and strange and they screw up the universe. So what will be the energy of the per unit length of the strings? Oh, I erased it. Why did I erase it? Well, I know what it is. It went as V to the 4th delta square. It had to, on dimensional grounds. Why do I worry? And V is 1 over delta, so it has to go as V squared. On dimensional grounds, E over L. Remember when I was doing the domain wall, so this is E string, E wall, that was over area, I said it has to be V cube, and it was. So in other words, the energy of the string that fills the universe of infinitely big strings, which infinitely to us is the whole universe, okay, would be V square R. Here, let's see if you remember the numbers, okay? Cosmology, you have to remember some numbers. This is to compare with the domain wall. The energy of the domain wall, which is large as the universe, was V cube. RU squared. It's constantly an applause. What's a ballet? Sort of, that's very amusing. You know, it's not so good that he keeps on talking, you know. And then you give the... So when I finish the class, I'll walk out and then you call me, you know how they do that. Okay, then I come back and open. We do it again. So who carries more energy according to you? What is your sense of numbers? Let's take phi 100 GeV. To understand E of a volt over E string is, if they correspond to the same physics, would be VRU. Is this big or small? What is your knowledge of the universe? It's big. The universe is very big. It's really big. It's not only that it looks to us.
How big is the GeV?
Oh, how big is universe in GeV? That's a good question. In inverse GeV, you mean? Very big. Well, you will see. GeV, centimeter, is 10 to the 14, or if you wish, centimeter, or 10 to the 13. Okay, let me not exaggerate, maybe 10 to the 13. There is a pi there. It's going to be pi times 10 to the 14. So centimeter is 10 to the 13, GeV to the minus 1. So it's enormous. 41, okay, very big in our units, okay? It's much bigger than, you know, how much bigger than the proton, okay? 41 orders of magnitude, okay? Bigger than the proton, it seems. Well, we'll put the numbers. This is 100 GeV. Yeah, we'll get a huge number, obviously. Times 10 to the 28, we decided, centimeters. So this is 10 to the 30. GeV centimeter is 10 to the 13. So this is 10 to the 33. See, wall doesn't carry much energy. It doesn't do much damage, okay? We got yesterday, wall, string. We got yesterday, the wall would carry some 10, 13, whatever orders of magnitude. The wall would carry nothing. The wall is irrelevant. Okay, why? Because universes. So how it goes? Okay, just to understand the energy of the universe, let's write it down. I'd like you to have the working knowledge of the cosmology. Yes, please.
According to me, the string has a smaller energy than the main one.
Sorry?
According to me, the string has less energy than the...
Yeah, 33 orders of magnitude.
Yeah.
No, 43. Yeah, sure. Well, it's not surprising. Universe is very big. It's huge. Huge in the units of GeV minus 1. That's what Mehmet was asking you. For the units of 100 GeV to the minus 1, it's very huge. And the wall goes as the radius square, and this goes linearly as the radius, so that's going to win. So you can ask yourself, why doesn't the universe in the form of baryons win? Why was it that the wall had more energy yesterday, right? Because the energy of the universe, how did we reason? Is the density of the baryons times the energy of the baryon times RU cubed. So you would say, well, that ought to win, right? It goes as RU cubed. The point is that this is very small. This is 10 to the minus 10 T cubed. GeV RU cubed. So it goes as RU cubed. T itself is not so, when you put the numbers, this was very interesting, okay. It turned out that the wall, it was not completely trivial then to compare the wall. This is the energy of the universe in form of the baryons, then the energy of the wall, okay, energy of the universe in terms of the wall, we wrote it is V squared, V cubed, RU squared. And then you have to put the numbers, okay, because this is very small in the units of GeV. So there your intuition, of course, is not sufficient. I'm not asking you, I wouldn't have known the energy of the string, how big it is. So I'm comparing to the wall because we did the wall yesterday. So we have some memory of what was going on. And we find out that the wall is negligible. So people even like the idea that there could have been strings at the beginning. The strings, some people like to think of strings as the seeds of inhomogeneities. Imagine that you form these strings in the early universe and these homogeneous use. There was a very popular idea some 20, 30 years ago. And it didn't, when people did numerical studies, apparently it's not so exciting. People found it much less exciting than thinking of inflation as a source of growth of inhomogeneity.
They're all requiring additional U1 base.
That requires some very unusual symmetry breaking in the early universe, right? The belief in a that will happen.
So that predicts another field, that particle.
Yes, of course. The study of topological defects is a sort of additional way of probing the possibility and the form of new physics beyond the standard model. Fortunately, in a sense, you said, oh, it's said that the standard model doesn't have these things, but then it's good because this way, if there will be a trace, if I find a monopole, something else is happening. It's not a standard model.
Why don't we talk about the same thing for broken SU2 in standard model? Is there a topological defect possibility? Or
Well, you can now tell me SU2, very good. So if I did the same thing for SU2, which I tried, and I look for such a solution as string, and infinity was circle, right?
Yes.
I've looked. So in order to have a non-trivial map, I can map a circle on a circle. Imagine that the field lives in the vacuum manifold of SU2. What is a vacuum manifold of SU2? S3. That map would be trivial. M0 would be S3. It's hard to visualize it, but think of that. Take S2. You can tell me, don't take SO2. Take SO3 broken down to U1, for example, just for simplicity. A smaller group. Then it's S2 vacuum manifold. But you know, you can always shrink the circle. There are no non-trivial circles on S2.
So we can't have any binding numbers from different sizes?
No, because the circle on the sphere can be shrunk. You cannot shrink circle on a circle. You see? So circle lives, you see, circle is topologically, there is a void here, therefore. A circle, in that sense, when I'm mapping on a circle, okay. But take a circle, and we always do this example, and then just take it smaller and smaller, it disappears. Doesn't matter how many times you go about that. And it's always zero. And surely on S3 also, which is of your interest. Okay, sorry, this is not the standard model. So you say, I really want SU2, this is S3. There are no non-trivial manifolds. Okay, the manifolds that you find non-trivial is S2 to S2, S3 to S3, 2 points as we did to 2 points. It's always the same manifold. And there are these topological characteristics of what it is.
But this non-trivial shrinking on sphere is some recent result, right? From the mathematical side. Like, there was someone who proved conjecture about...
No, this can't be recent. That you can shrink, that I can't believe, so recent.
I think there is a conjecture called quantary conjecture that says, like, topologically, if something is equal to sphere, that should happen. Every circle should be shrunk to a point. But
I can't believe that. You mean if you ask this guy in the other room, Euler, in 1772 that he wouldn't know, that he wouldn't see them, but that you don't need. So maybe the languages, you just take, you know, you don't have to be, you can ask your grandmother to put a piece on this, and you can show to her that you can shrink it and nothing happens. That I think it's not convincing me.
I don't know, like topologies.
You see, if I take a sphere, I have to cut it. I have to take scissors, and then, of course, then I may not be able to shrink anymore. That's sort of interesting if I have, right? Because, but then that's not a sphere, right? Imagine I cut it, so I got now a circle cannot be shrunk. I take a football and I cut it here. Now this circle here cannot be shrunk, okay, because there is a hole. But this is not a sphere. So if well, I don't know. I wonder what it is. Maybe people didn't think of probably wouldn't. Okay, I don't know how this homotopy topology reasoning may be right, but they would be phrased in a different manner. Probably people would know. I would imagine.
You say point-wide conjecture. I think it's about if you have some curve in 2 dimensions, you can continuously deform into a circle. And then it's like the conjecture is like you can do it for a general hypersurface in any dimension. If it's closed, you can continuously transform into S.
Yes, but I heard
that's the conjecture.
It's almost for every dimension proven, but for 3-dimensional surfaces, if it's like equal to some sphere, it was open and
This is not this is a trivial result we're talking about something. Yeah. Is there something to summarize? Let me think, I'm not sure. I raise this in order to think whether what did we learn? Okay, maybe we could summarize what were essential features. We had U1 spontaneously broken. The vacuum manifold was a circle. Infinity manifold is a circle if I look for a cylindrically symmetric solution, so then it's not surprising that it can exist a cylindrically symmetric solution, because I can map these guys, right? And the crucial thing was, by asking that phi infinity once again belongs to M0, gave us AI to go, okay, it's here. Everything was here. That was our strength. That was sufficient to say at infinity. That gave the flux. The integral of ADL, then it's not anything. There is a flux. Of course, the reason there is a flux is not that because if this was true everywhere, nothing like this would happen. There was a singularity somewhere. We found out that the strings is actually made of Higgs field. And every time the same thing will happen. This was a domain wall. We got something interesting, some magnetic field. This magnetic field is not the magnetic field you and I used to. Okay, this was creating problems for you to have an intuition of what was going on. The crucial thing is that inside, this is the right thing to say, phi is phi maximum, let's say. It's away from the minimum. So it's interesting, these topological defects. You see, because they are made out of phi, their energy momentum tensors are very unusual. I can just mention it here briefly that for domain wall and string, you find your energy momentum tensors. And they have I won't derive them here, okay? But you know how to find the energy momentum tensor from a Lagrangian. There is a well-defined procedure that probably you have energy and momentum. You know the night. So the energy momentum of domain wall, it's interesting. There is a density, but there is also pressure. there's a pressure inside how to say it? You know, it's not a wall like this. Here there is just density, okay? Pressure is zero. Okay, when we speak about material objects, they have basically pressure zero. How to understand it? Maybe to give you a feeling, okay? This we can chat maybe for a minute to give you a feeling. Imagine, forget it's even more sophisticated. Let's just take vacuum. What is the energy momentum tensor of vacuum? Right? Nothing else. That's the only thing. I don't have to compute it. You can compute it. Use whatever knowledge you have. You will see that it has to be that on the symmetry of the problem. Vacuum was a configuration of a static value of the field, right? In our spontaneous and broken theory. Okay, that I write the potential. So let's now I write potential like this. But I should actually add V of 0 because I don't know what it is. So you did the Big Bang, right? The ideal fluid, right? And it has, when it's radiation filled, the universe, it has pressure. Pressure is related to energy density. It's a third of energy density, something like this, right? Maybe okay? Notice in this case, okay, pressure, there is a G0 component, this is rho, and then there are GI components which are pressure, right, in the fluid form. Just think of the analogy with when you study Big Bang. This guy will become as a very unusual fluid. It would have Px equal Py equal Pz equal minus rho. When you go to the Newtonian limit of Einstein, when you just study some Newtonian limit, what happens when we move in a gravitational field? You and I slowly, light objects slowly move in a weak gravitational field. The thing that matters is the trace of the mu. Okay, so what determines the Newton potential, Newtonian limit, you have to think of that it's not rho, it's T mu. So let's say like this. Or T mu. Am I right? T mu or?
Yeah.
Some, whatever. Yes. So what we are using, our intuition, of course, is the system where pressure is zero. And then we know what happens, right? Gravitation is attractive because rho is positive. Okay? Energy density, this is made of some stuff. Positive stuff, and this attracts us. But T mu may be negative when you have pressures which are, for example, if you had pure vacuum, you will see that T mu is negative. A vacuum would give you, this is called inflation. Inflation makes the things grow out of nothing. Okay, but you didn't study inflation, okay, but it's a pity, but anyway. So what I mean is that when you write down T mu for the domain wall, you will find out that there is pressure inside it. It's a relativistic object. So in this case, T mu mu is negative also, the domain wall. Domain wall, it's not a wall like this one, it would be repulsive. This is how we would know that something crazy is happening. Imagine, this is fantastic. A static domain wall would just push us away. Very, very unusual. The interesting thing of the string is T mu mu, so for the wall, for the string, is actually 0. There is a pressure only in one direction because wall has only one direction and it has minus rho. By the way, everything is given by one and the same quantity. There are no, like here. Here there are 3 pressures, but they're all given by the same rho. Okay, this is the, because there is only one scale, if you wish. In every problem there is one scale. So you understand what will happen with the string? No force whatsoever. There is a string full of matter. You just don't know, you feel no force whatsoever. Have a look if you wish, if you're interested, this, or ask me, have a look, it's in my notes. I think at least I do the wall. Another interesting aspect of this topological difference, the gravitational pull. Okay.
So, I don't understand. Like if we have a wall, kind of a spherical wall, it will push things towards the center?
Or the spherical wall.
Or is it?
What will happen in a spherical wall? This I told you for an infinitely long wall. Good question, what happens in a spherical wall? If it's large enough, then my approximation is good. It's irrelevant. If it's really spherical, like small, I don't know.
Oh.
I have to think. I don't know.
But these walls will repel things. Like
you and me. I'm not saying it will repel each other. That I don't know. I don't know how they behave when they find another object, which is very strange. The way they are acting, when I take the Newtonian limit, I take it acting on the states of something which has some density, which is not large, slowly moving. I go to non-relativistic limit. This is how to view Newtonian limit, and there is only rho. So that the only thing is. People may have found some, in the case of the string, there may be even some exact results. More interesting, how they act on relativistic bodies, or maybe even how a string acts on a string. The reason I'm mentioning it sort of as a nice example how our intuition fails completely when we think of these extended objects, this classical solution. Their properties are unimaginable because they are made out of relativistic scalar field. So you see, imagine what does it mean that there is a pressure which is negative? We don't even know what it means. Right? It's not the situation we encounter. Therefore, this is the vacuum. Okay, this was the people found out. Okay, there is a great, beautiful paper by Alain Wood in 1980 worth reading. Fantastic. Which I find also very tragic because it failed completely. The reason I don't work on inflation because there is no theory to me of inflation. Your people around me tell you they write some silly little models. By putting some silly little scalar field, they say, oh, I have a model, I have m squared, phi squared, where m is very large, says one guy. The other guy says, no, I have a model, it's lambda phi to the fourth, but lambda is very, and it's the same guy, usually called index. Anyway, I find it, it hurts me when I hear that this is called a model, you understand? It's not even a toy model, it's a piece of a field which has nothing to do with particle physics. What Alan would imagine, he took an SU5 grand unified theory, wrote the most general potential, which has a cubic piece also, which I didn't bug you when I mentioned the problem. If he found out that you can be caught in the false vacuum in the early universe, then you have to study what happens at high temperature.
Like a higher vacuum, something like that.
There is a vacuum which is not ours, and you will get caught, if you get caught in this, and imagine that this dominates over, there is always T to the fourth, right? In the early universe when it's hot. But if you have the temperatures below the scale of that thing, you will get this exponential expansion. You would understand why the universe is so large. We have a deep problem. Okay, I'll finish on this note so that we can talk about magnetic monopole. We have a terrible problem to understand. The universe is just too bloody large. They cannot be. What does it mean? Remind me, what does it mean? Large in what sense? It was not in causal contact with itself. That cannot be. It has one and the same temperature with a precision of 1 in the 10 to the 5. Okay, it's not maybe roughly, okay, so it's perfectly one, it's homogeneous and isotropic, crazily enough, okay, to a great precision. Occasional galaxy here and there, but who cares? Which spoils that. You know, if you look at large instances, it's isotropic and homogeneous. So in order to understand that it cannot be, right, the universe must have started from some causally connected domain, which was at the level of the horizon, and then somehow it grew very large. There must have been a period. So it's hard to believe that it's not true. This is beautiful inflation, okay? I, for one, would surely, what I find very painful that this didn't work, unfortunately, okay? This beautiful thing, the same grand unified theory that give you magnetic monopoles, I would proton decay, so on, will also give you a mechanism for inflation, which is the same field. So it's not just some model you're writing, it's the same field which is responsible for all of the new physics. Imagine, it's like in the standard model, imagine that it's the same Higgs field that is doing what it's doing, it's also doing inflation. Then of course you get excited because now you can check it. The trouble was that you never stop inflating. Inflation took place in the past, it seems. But also we know that it stopped because universe is a big bang. Universe is not inflationary, as we know. When we trace it back to the temperatures of MEV, it's Robertson-Walker-Friedman standard Big Bang cosmological evolution, which is very slow, nothing exponential about it. Okay, so the same way that and you can see it here, understanding that you have this funny negative pressure, topological defects have this funny negative pressure, we can basically stop here. If there was time, I would do it, but then it's sort of, it's a digression, as beautiful as it is. So we come back and do the monopole. And we get a cup of tea. Coffee. Oh yes. Thank you.